Hey everyone, welcome back. So for our last named probability distribution for discrete variables, I want to take a look at the Poisson probability distribution. And again, this is one that's very well known, very commonly used for making predictions about variables that can reasonably be expected to follow this type of distribution. So what is a Poisson distribution? Well, it is useful when we want to try to make an estimate or estimate probability for the number of occurrences of some event within some defined area of opportunity. And so what is an area of opportunity? Well, it could be a lot of things, but typically it is going to be defined as some type of area within which an event can occur. And so if we're talking about an event that maybe occurs over time, then it could be an interval of time, such as a minute or an hour or a day or a 30-minute period. And we're interested in some sort of event that is occurring within that area of time. Or it could be an area of volume or an area of uh, an actual area of real estate of some sort. Um, and we're interested in some event that impacts that particular area. So a few examples here, number of scratches in a car's paint. Or if we want a very Lubbock example, maybe I could say the number of hail dents in a car's paint. And so we can use the use the Poisson distribution to predict for a particular car that was subject to a hailstorm, how many dents would we expect to see? And what is the probability of getting those certain number of dents? If we define an area of opportunity as being a person and we're interested in mosquito bites, right? We could identify the number of mosquito bites or predict the probability of a certain number of mosquito bites per person. Here's an example occurring over time. If we are interested in predicting the probability of a certain number of computer crashes, maybe we define our area of opportunity as a day. And of course, we can increase or decrease those areas of opportunity. So we could go from a day to a week, or from a day to an hour, right? Or some other interval of time. So these are some of the types of things that we can use the Poisson distribution for. By the way, just a little historical side note here. The Poisson distribution is actually named after the statistician who developed it, and he actually used it to predict the probability of death from being kicked by a horse in the Prussian army. So, yeah, little historical tidbit for you there regarding the Poisson distribution. All right, so what are the characteristics of the situation that we need to have? Well, we're interested in predicting the number of times some event occurs within whatever we have defined as an area of opportunity. Now, the distinction between the Poisson and the binomial are fairly similar in that we're looking at the number of times an event occurs and making a prediction for the probability of that. But the key difference is with the Poisson, we don't necessarily know how many trials we have, where of course, as we saw previously with the binomial distribution, we must know how many trials we have, and we're going to predict the probability of X successes out of N trials. With the Poisson, what we're predicting is the probability of X successes within some area of opportunity, depending on how we've defined it. But we don't necessarily know how many trials they are. What we do have to know for the Poisson is what is the historical average number of successes per area of opportunity. And that's really the key parameter for a Poisson distribution. And that's the parameter that we call lambda, which is average number of events per unit or per area of opportunity, or as I described it a moment ago, the historical average for each area of opportunity. And that's what we use to make our predictions from. Just a few characteristics. We need to be able to assume that the probability that an event occurs within an area of opportunity is going to stay consistent over different areas. We need to be able to identify that the number of events in one area of opportunity is independent of events in some other area of opportunity. And then also we need to be able to be reasonably sure that as the size of the area of opportunity changes, as it becomes smaller, then the probability that we'll have multiple events within that area becomes smaller. As it becomes larger, the probability that we'll have multiple events within a single area becomes larger. So we have to be reasonably certain that that will happen. So, but if we can reasonably assume these characteristics, then Poisson can be a very useful distribution. All right, so let's kind of take a look at it. Again, that historical average, or lambda, is the key parameter. And in fact, the mean of our Poisson distribution is going to be equal to our historical average, as well as the variance is going to be equal to our historic average. And then, of course, our standard deviation is going to be the square root of that variance, where lambda is the expected number or historical average for the number of events within an area of opportunity. All right, let's take a look at the formula, and I am not going to work through this formula with you. I show it to you so you can see where it comes from. But what this formula is saying is that the probability of the number of successes being equal to the number we're interested in, given a specified lambda or a specified historic average for the distribution, can be computed by taking E, or Euler's constant, raised to the power of negative lambda times lambda to the power of x over x factorial. Again, E, or Euler's constant, is the base of the natural logarithms, which is approximated as 2.718 and change. And of course, if you wanted to plug in, actually I think I do have an example here where I have the numbers plugged in to that formula. If you wanted to plug those in, you certainly can do that computation. The example we are looking at here is arrival rate at a fast food restaurant, and Poisson distribution is frequently used to predict how many customers or how many of some event will occur within a period of time. So the period of time is our area of opportunity, and in this case what we've done is we've specified the period of time as being a minute within the period from 11 to 11:30. Why are we being so specific about 11 to 11:30? Well, if we're talking about arrivals at a fast food restaurant, the number of customers who are arriving every minute during the lunch rush is going to be very different from the number of customers who are arriving every minute, let's say in the middle of the afternoon. And so we do want to make sure that the areas of opportunity that we are making predictions for are similar enough so we can assume a constant historic average or a constant lambda. So, in this particular situation, we've determined, okay, from 11 to 11:30, we're seeing an average of 1/2 customer, 0.5 customers per minute. So we can use that as a reasonable estimate of a constant lambda or a constant average over those 30 areas of opportunity. So the question that we then want to answer is, all right, well, what is the probability that we get exactly 2 customers per minute, or in a randomly selected minute for this during this area of opportunity? All right, so we are predicting the probability of getting an x of 0.2 given a lambda of 0.5. Plugging that into our formula, e raised to the negative 0.5 times 0.5 squared over 2 factorial. If you work through the math, that comes out to be about 7.6%, 0.0758. And like I say, again, the function, this formula definitely works for you. However, I'm typically going to use a function in Excel to do those computations for me. And so the function that we use here is going to be Poisson.dist. Notice that this is similar to binom.dist that we used in the previous video with our binomial distribution. And what we're going to see as we move forward into some of our other topics, we're going to see other Excel functions that we can use to make these types of computations. And what you're going to see is that anything that ends with a .dist, any of these functions that whose name ends in dist like this, they are going to predict a probability for us. And so it's nice to have that assurance of how these functions work. But in any case, arguments that we need for the Poisson.dist, the number of occurrences we're interested in making a prediction for, the lambda or the historical average for the distribution, and then again there's a logical argument that we will indicate as true if we want to get a cumulative probability and false if we want to get an individual probability for the specified number of occurrences. So I am going to jump over to Excel, and I am on the Poisson tab of the class demo file. And what I've got in here is, again, I've set up possible numbers of successes for my probability distribution. And so I started at 0, can't have less than 0 customers arriving in any 1 minute period. Started at 0, and I decided to go up to 6. Why 6? Well, it seemed to be large enough so that the likelihood of getting 6 customers in any randomly selected minute is going to be pretty darn small if I only get 1/2 customer per minute on average. But if I needed to go larger than that, I certainly could. So I've got my lambda value, my historical average, up here in cell C1. And I'm going to, starting in my first probability here in my distribution, I'm going to go ahead and compute the probability of getting exactly 0 customers. So go in and search for my Poisson function, and the one I want to get is Poisson.dist. The arguments that I need to give it are the number of successes I want to make the probability computation for. I need to tell it where to find the lambda, and I'll make that an absolute cell reference. And then I'm going to enter false for the cumulative argument to tell it that I want the probability of exactly that number of successes, not the cumulative probability. So go ahead and enter that, and then I'll copy that down. And you'll see that the probability of getting exactly 0 customers is a little over 60%. The probability of getting 1 in any randomly selected minute is about 30%. Here is the probability of getting exactly 2, and you'll see that that 0.0758 matches the 0.0758 we had on our slide here. And again, you can verify that arithmetic and be sure that this arithmetic matches what we see as the result of the formula here. So, you know, if we on average get 1/2 customer per minute, the probability of getting 2 in any randomly selected minute in that, that time period is definitely present, but we're getting smaller. The probability of getting exactly 3, possible, but it's fairly small. And then as we get up to larger and larger numbers, then that probability drops off to essentially 0. We've also got our chart showing showing that probability distribution. And you can see with a reasonably low lambda, like 0.5 customers per minute, we wind up with a right-skewed distribution. Now, let's go back and remember our characteristics of a discrete probability distribution, and we can verify that indeed all of the probabilities we have computed fall between 0 and 1 inclusive, and we can also go ahead and compute the sum of those probabilities, and we can see that indeed they do sum to 1. So this distribution does in fact meet the characteristics of a discrete probability distribution. The other thing that we can do is go ahead and make some of these computations, and there's not a whole lot of computations to make, but we can make computations for our mean, variance, and standard deviation. All right, so our mean, of course, is just lambda. Our variance also is just lambda. And then our standard deviation is going to be the square root of the variance So I can make that computation using my square root function, and I can see that the square root of, or excuse me, the standard deviation of this distribution is going to be 0.707. Now, again, these numbers don't necessarily tell us a lot in and of themselves, but they can be very useful for comparing one distribution to another. So worthwhile to know how to get those. The last thing I want to look at with the Poisson distribution is how that distribution changes as the parameter lambda changes. So we're starting out with a lambda of 0.5. Let's go back here to our spreadsheet, and let me change this lambda, and you can see as I change it to, let's say, 1, then our higher numbers of customer arrivals per minute start to become more and more likely, right? And so here 6 has a probability of 0.0005. So very small probability, but some probability of getting 6 customers. And we can actually kind of see those, the columns for 5 and 6 start to appear on our chart. If I were to go to 2, then we start to get more likely, all right? If I go up to 3 average customers per minute, then the probability of getting exactly 6 when I have an average of 3 is a little over 5%. And at this point, what I might start thinking about doing is extending the values that I'm showing, the possible number of successes that I'm showing in my table, because now I'm no longer accounting for all the possible values. So I might want to make my table a little bit longer. But what you can see, and you can really see this in the shape of the distribution, is that as that lambda increases, then our distribution becomes more and more symmetric. All right, so that fairly short and sweet look at the Poisson distribution, and this is one that has applications for this type of problem, arrivals per period of time or occurrences of some event per area of opportunity, and it also does play into a lot of statistical modeling as well. So I'm going to go ahead and wrap up this video here. And this also wraps up our look at discrete probability distributions. Please let me know if you have any questions.